Are we ready to start? Great. Okay, so today we are going to continue from where we stopped last time. If
גוגל פתוח או שאני אשלח אותה?
אין מושג. Okay, so today we want to continue our tutorial from the previous time. Now we are going to speak about equilibrium. So what is equilibrium? Equilibrium is achieved when all the intensive parameters are equal. So it means that if we have, for example, we have some kind of a box which divided by two subsystems, and now we are allowing to several things to happen. First of all, we are allowing heat to transfer between the two subsystems. For example, this is subsystem 1, which is defined by several parameters like energy, volume, and number of particles. And we have subsystem 2, which is defined by internal energy U2, volume V2, and N2 particles. So at the beginning, we have a barrier, and we are not allowing anything to pass through, not heat, not particles, and the barrier can't move. So it is in its place. Now, what we are going to do is we are going to allow only heat to transfer between the two subsystems, and we wait. So now heat can transfer between the two subsystems, and we wait until we reach equilibrium. So what will happen when we reach thermal equilibrium? Someone can guess. Someone knows maybe. What happens? So in thermal equilibrium, what we have is that the temperature in subsystem 1 will be equal to the temperature in subsystem 2. And now, on top of that, we want to allow, for example, that particles will be able to move through the barrier, not only heat, also particles. So what will be the intensive parameter that now will be equal in equilibrium? Because n is what can move. So if n can move, so in equilibrium, what will be equal is the chemical potential, mu. Okay. So what I am showing you now is that what happens when we have equilibrium. If we have equilibrium due to heat transfer, it implies that the temperature will be equal. If we have equilibrium due to particle transfers, so what it implies that the chemical potentials in the two subsystems will be equal. And now, on top of that, I am allowing to the barrier to move, okay, due to pressure. So the barrier can move to here, or it can move to here, and when it reaches equilibrium, it will stop moving, right? What will be the intensive parameter that now going to be equal? Think again, what is changing?
Pressure.
pressure is changing. Wait, yes, but what is changing due to the when I am moving the allowing the okay when I am allowing the barrier to move. So what is changing is the volume, right? And then it will stop when what will happen? When the pressure is equal. Pressure. The pressure. Okay? P1 and P2. Okay? And this is conditions for equilibrium. If we have equilibrium, then this is what it implies. Let's do an example. Now we are going to do an example on this drawing. So now we have a barrier. And I have two subsystems that are not interacting. Subsystem 1 has an internal energy U0, volume V1, and number of particles N0. Subsystem 2, on the other hand, have internal energy of 2U0, volume V2, and the number of particles is 2 N0. At the beginning of the process, the two subsystems don't talk to each other. Now, we are going to allow, okay, we are replacing the barrier in a barrier that conducts it. Okay, so now we are allowing thermal interactions through the barrier, which means that heat can flow from subsystem 1 to subsystem 2 and vice versa. And we wait. We are waiting, and we know while we are waiting for the equilibrium to happen, we know that the entropy of each of the subsystems is described by the following equation: A U1 at the power of alpha, V to the power of beta, and N to the power of gamma. And we wait. Now after we finish to write the equations, the two subsystems finally got to a new equilibrium state. And the question is, A, what is the internal energy U1, U2 in the new equilibrium state?
אפשר שאלה בעברית?
Yeah.
האנטרופיה שהכרת זה במהלך כל התהליך כאילו הביטוי הזה, או שרק בהתחלה כאילו זה הביטוי לאנטרופיה?
Okay, so I will translate it for those who don't know Hebrew. So what is your name? So what Ayelet asked is whether this entropy will be true for the whole process, not just not just in the beginning, but even after reaching equilibrium. And the answer is yes. Okay, this is true for the whole process. Okay, this is the entropy that describes this kind of subsystems. Okay, so now we want to know the new energy, the internal energy of each system. So what we are going to do, first, we know that U, which is the energy of the two subsystems combined, will be U1 plus U2 equal to 3U0, because the energy is conserved. Okay, this is a closed system, And now we know what is the what. Okay, so now we reach the equilibrium due to transfer, due to a contact, due to a barrier, heat conducting barrier. So what is the intensive parameter that will be equal now?
Temperature.
Did you correct? Okay. So thank you, I get it. Now the temperature due to the new barrier heat conducting T1 will be equal to T2. And now we want to know what is T1 and what is T2. We need to find out. So how can we find out? We have the equation that describes the entropy, and we want to describe T with entropy. So using the first law of thermodynamics, we know that du is equal to T ds minus P dV. This is, we don't have any mechanical work, so this is 0, and this is equal to T ds when it's true. Right. Okay, this is a quasi-static process. This is the assumption. Okay. No, but even if we don't say so, it's a quasi-static process. Okay? Okay, so now we know that T is equal to du ds for V constant, and this means that 1 over T is equal to ds du for V constant. Voila, this is what we want. Okay, now we can take the derivative of s with respect to u, and we have and we can compare. 1 over T1 is equal to 1 over T2. I am going to only write the final result. Okay, so now I have equation 1 and I have equation 2. Two different equations, two equations for two variables. And therefore, I just need to isolate u1 or u2 and find out. And to solve the equation, and the final result is going to be u2 Okay, so this is the result of subsection A. Any questions on the topic? Subject? everything is clear? Okay. Okay. Now we want to know how much heat has been transferred due to the process. What is the condition that heat transferred from 2 to 1? Okay, so what we know? We know that delta U2 is equal to minus delta U1. This is one thing that we know. And we also know that delta U is equal to delta Q, right? Minus delta W, but there is no mechanical work, so it's just 0. And delta Q is equal to delta U2 is equal to U2 minus 2U0. And that's it, we just need. So our condition must be that this is less than 0. And then this implies that so this is the condition. So it means that we need to have some kind of a condition about the volumes, the ratio between the volumes. Okay, nice. Any questions? Okay. Does anybody wants to ask something? Feel free. You can ask in Hebrew and they can translate it if you feel uncomfortable. Okay. So now we are in section C. Okay. Now, so up to now, we have dealt with two subsystems that interacts due to heat transfer. Now we are going to do tiny holes in the barrier. And now not only that we are allowing heat to transfer, we are also allowing particles to move through the barrier. So what will be another equilibrium that we are going to have? Correct. Okay, so mu1 will be equal to mu2. Let's keep that in mind. And now what we have been asked to do is to prove the following ratio, we need to prove that P1 divided by P2 will be equal to X, N1, N2, and find out what X is. X should be a function of V1 and V2. Does the question clear? Understood? Do you understand what has been changed now?
Particles.
Yeah. Okay. Now particles can move.
Heat. Also heat.
What?
Also heat.
What?
Energy.
Sorry.
Energy and the particles can translate.
Yes. Okay. Now also energy can change, and also the particle can move. Okay.
למה X צריך להיות תלוי ב-V?
This is what we have been told. Okay, we will see. But intuitively, this is the only variable that don't change. So this is the only thing that we've been told. So, as Ayala mentioned, now that now in the new equilibrium state, mu1 will be equal to mu2. So does anyone know what is the meaning of mu in the beginning? To begin with, what is this means? I mean, we know the T. What is temperature? If we want to define temperature, then what is it? Yeah, but intuitively, it's just the kinetic energy, right, of the particles, the average kinetic energy. And P is the force per unit area that they are applying, right, due to change in volume. So what is mu? Mu is how much it's hard to add particles to the system. Okay? Basically, if I add one particle to the system, how much energy it will cost me. So now, how to begin? We are going, as always, to the first law of thermodynamics, du Tds minus Pdv plus mu dn. So this is 0, and mu is equal to minus T dou S dou N for constant volume and constant energy. I am going to basically 0, but here it's 0 because I'm taking it to be constant. Okay? So if mu1 is equal to mu2, this means that A1 alpha, B1 beta, gamma N1 gamma minus 1 is equal to A U2 alpha A1 beta gamma N2 gamma minus 1. So this is one equation that I am going to use, and the other one is, of course, I want to relate it to pressure. So P is equal to T dou S dou V, U, and N is constant. So now P1 divided by P2 is AU1 alpha multiplied by BV1 beta minus 1 N1 gamma AU2 alpha beta V beta minus 1 and 2 gamma. This is the second equation. And now I'm just going to isolate u1, either u2, and u1 and or either u2, yes? And just insert it into this relation. And what I am getting, and what I will get, is that the ratio is equal to V2 divided by V1 multiplied by N1 divided by N2. Piece of cake. Okay, so this was it. Any questions?
למה יש כאן מינוס במיו?
Okay, so Ayala asked where the sign minus came from. So I just, if I am going to take the derivative with respect to constant u and constant v, so this is 0 and this is 0, and this goes to the other side, right? And then this is minus TDS, and then I'm going to divide by dn, and that's it. Okay? Okay, so if there are no other questions, so I will move forward. Okay, now let's talk about compressibility a little bit. And as we saw, the compressibility kappa of t is defined as minus 1 over v, dou v dp for a constant t, and this is greater or equal to 0, right? Correct? Did you saw this? You will see, I am guessing. This is just a relation. And now we want just, I'm going to show you just a little example about how to use it and what it can implies to us, what it can tell us. So I want to prove that the heat capacity due to constant pressure is greater than the heat capacity due to constant volume. This is what we want to show. Okay. So let's start and see where the road will lead us. I just want to write here that the definition for heat capacity for some variable is dq to dt, and with respect to a constant x, and that dq is equal to du plus dw Okay, let's start. So CV is, as we saw dq dt with respect to v. Let us insert the definition of dq, du plus p dv, dt, v constant, du dt v, but we know that du is t ds minus p dv, so cv is ds is t ds dt v. Okay, this is CV. Now, for CP is the Q dt for a constant P. So this is du plus P dV dt for a constant P. And this is T ds minus P dV plus P dV dt for a constant P. This cancel this, and Cp is T dou S dou T Okay, so we also found out what is the heat capacity with constant P, and now I want to relate those two quantities because I want to know, okay, I need to show that this quantity is greater than this quantity. Okay, this is my goal, and eventually I'm going to use the compressibility somehow. I'm just telling you where we are heading. And now there is we are going to start some kind of a game with the differentials, and we're going to show this connection holds. Okay, so ds is dou S dou T dt plus dou S dou P dt. Sorry. Okay. Now, in order to relate this, let's use a constant volume. So the differential dsv is equal to dsv dt p dtv plus dsv dou p dpv.
מה זה SV?
Hmm?
מה זה SV?
The entropy due to a constant volume, with respect to a constant volume. So now dsv dtv Okay, so from here we extracted this property. And why it's important? Because now I have this. Now I know that dou S to the T P is equal to now we have this relation, which is exactly this, right? Okay, can you see it? אז מה? יכולים להצטרף.
אני יכולה להניח את הדברים?
כן. איזה קורס יש פה אחר כך?
נבחן את החוויה.
לא להפריע לנו. אוקיי, so...
אתה יכול להגיד רק למה למעלה זה DT ו-DT?
what?
זה DT ו-DT או DT ו-DT?
איפה?
בשורה העליונה.
פה?
לא, שמאלה? אחד שמאלה? כן, כן.
מה להגיד פה?
מה כתוב שם?
Okay, so Elliot asked me to say what I wrote. So I wrote ds is equal to dou s to dou t with respect to a constant pressure, dt plus dou s dou p with respect to a constant temperature, dp. Okay, then I followed the I developed it. Then I said that this is with respect to a constant volume, okay? And this is with respect to a constant volume, and then it's just with using subscript of v. And this is and then I divided by dTV, and I got dou dsv to dTV, this relation, okay? And then I transformed it into a partial derivative, and then I just isolated this quantity here that I want. Okay. Now I'm going to insert it in CP. So CP is just dou s dou t v minus dou s dou p t dou p dou t v, and using one of Maxwell relation, I am getting t dou s dou tv plus dou v dou tp dou p dou tv. Okay, this is a relation that I got for the heat capacity with respect to a constant pressure. Now we are. It seems that we are ready. So Cp minus Cv. Take note that this term is going to cancel out with this term. Okay. And all that we are left with is dou v dou tp dou p dou tv. Now I'm going to use the cyclic rule, which is state now Cp minus Cv is just minus T dou V squared dou P dou Vt. But what is this? This is just 1 over this. It's just 1 over kappa T. This is just equal to 1 minus V kt. So Cp minus Cv is equal to T kappa T dou V greater than 0. That's it. We have proved the relation. Now, whenever you need to use it, feel free. If you will ever need this relation. אוקיי? כן, בטח.
למה החלטת ב-DS לעשות דווקא לפי, נגיד, כאילו לגזור לדו S לדו T ולדו P ונגיד לא לגזור אותו לדו P?
Because I want. Okay, so she asked why I decided to do this in this manner. So it's a simple answer because I know where I want to go. I want to relate this quantity to this quantity, right? Because as it seems to us now, it is to compare apples with oranges, and they want to compare apples with apples. So I need to transform it somehow, and I am starting the transformation, and then I see that here there is some kind of quantity. Here there is some kind of a quantity that I can use if I will do the transformation that I actually did at the end.
כאילו, אבל האנטרופיה היא כאילו תלויה בהרבה משתנים, לא רק ב-T ו-P.
In this case, it also depends on V, but I took it with respect to a constant V, so there is no differential in V because the V is 0, because V is constant.
ונגיד, למה לא לקחנו כאן את החלקיקים בחשבון גם כן?
Because you could, but then I would thought instead of only V constant, I will also tell that the number of particles is constant. Because there is no useful information in this. It won't lead me to where I want to go. So, okay. Any more questions? Okay, so we finished. Thank you for listening, and see you next week. Michal will see you next week.
תודה.
יש לי שאלה לגבי חוסרי כללי, כאילו מה גורם לזה להיות כל כך קשה?
מה זה?
לא, כאילו, מה גורם לקורס הזה כדי להיות כזה בין הקורסים הכי, כאילו, בין הכי קשים?
לא יודע. מבחנים מאוד קשים, והבחנים גם די קשים של סטאס.
אבל זה כאילו חומר קשה, אז מבחנים קשים, או זה כאילו, וגם הקושי זה המתמטיקה, זה
תראי, שום דבר לא חייב, כאילו גם הקורס הכי קל שיכול להיות בעולם יכול להיות מאוד קשה אם ייתנו שאלות קשות, לא יודע. תני לי קורס שהוא נחשב קל. איך?
מבוא למחשבים.
אוקיי, אז אם עכשיו מבוא למחשבים הייתי מבקש ממך לכתוב כאילו איזשהו קוד פסיכי במבחן, או אז היית אומרת בוא'נה איזה קורס קשה, נכון?
אז הקושי זה במבחנים, כאילו
הקושי זה במבחן, כי המבחן דורש הבנה. כאילו, לרוב המבחן דורש הבנה ותרגול שמקבלים בתרגולים, ולשאול, כאילו להיות על החומר, כי במהלך המבחן, להיות על החומר, כאילו צריך להיות על החומר כל הזמן, כדי למקסם את המבחן. וזה קורס קשה באופן כללי, כי מכניקה סטטיסטית זה לא קורס קל. באופן כללי. אבל אני יכול להגיד לכם שלדעתי זה אחד הקורסים הכי מעניינים בתואר ראשון.
גם מרגיש לי שיש פער בין שיווי משקל, בין האקולוגיה, בין כימיה לבין פיזיקה.
מה הכוונה? מה הפשט?
כאילו, מרגיש לי שיש כאילו הבדלים בין איך שמלמדים בין המחלקות.
אנחנו מלמדים מתמטיקה, כי אנחנו עושים מתמטיקה, בכימיה לא עושים מתמטיקה.
לא, כאילו שמה זה כאילו...
יאללה.
ההמון זוהם עלינו, אז זה נמצא.
רגע, פה, קצת פה.